Okay, guys. Hybridization warm-up key. There was an error there that somebody caught. At the very bottom. Isn't there an error here somewhere? I don't know if I've already fixed it or what. Was there an error here somewhere, somebody? Somebody? Which one was it? Okay, there's an error there somewhere. We'll look at it next time. I think I've already corrected it. We have the alkanes handout and the blue sheet. I have an extra blue sheet. This was sent by email. Okay, I'm pretty sure we did not do this nomenclature on the video. So, last Wednesday, I think you said we did, but I'm pretty sure we did not. Let's do this on nomenclature here. Longest continuous chain, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a 10 right through here. Is there another 10 anywhere? One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't think there's another 10 anywhere. Longest is 10, so that is what, decade? 10 years, decade. Decade. What's on the decade? What is this here? It's a propyl. Okay, it's a 3-carbon fragment. Propane, but we name it as propyl because it's a substituent, the YL ending. What is this here? That's a complex sub. It's 1, 2, 1, 2, 3. It's a propyl, but it's got a methyl on it. In one position is the first carbon coming off the main chain. That's 1, 2, 3. There's your propyl. At the one position we have a methyl, and so this is a 1-methyl propyl. Okay, it's a complex sub. Like that, and we have a propyl. What's the one position of the main chain? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Either way you go, it's 5, 6. So how would we decide?
Alphabetical order.
We'll let it go alphabetical. And so M comes before P. So we're going to make this 5, 6. So the name is going to be, at the 5 position, we have that thing in parentheses. And then at the 6th position, we have propyl. And then we have decane. And this is all one word. 5, 1-methyl propyl, 6 propyl decane. How does that look? Were there any questions on that page? Common subs? Nomenclature on test 1 will be first page, and including the alkyl halides. What which are named just like the first page. It's just the halogens are named as substituents. Did we do this one on the video? We did that one on the video? Alcohols and below will not be on the test. This just gives you an idea of some of the nomenclature. I cover nomenclature of alcohols and organic 2, etc., all down the line. But it's sort of very analogous. You're going to have a sort of a group carbon chain, 4-carbon chain alcohol, 4-carbon chain with the OL ending indicating alcohol. That's standard. But alcohols, ethers, and amines, that will not be on test 1. Just a systematic nomenclature, including alkyl halides. Should be pretty straightforward. If you have questions, please ask. Should be questions in your textbook for practice. I think you left off here these condensed formulas, which are not pure formulas, but they have some structural information in them. You'll be able to decipher these. How do we do on the one on the here, guys? You guys on the right. Well, let's do it. We got 2 methyl. We got 3 methyls. 3 methyls on a carbon. So we got a carbon with 3 methyls. And this carbon binds to another carbon. And this carbon's got 2 methyls. Then a CH2. And very often that's shown condensed. I'm not going to draw off the bonds, but that's HH, right? And then CHO. CHO. No. H doesn't make 2 bonds. What is this ending here?
Carboxyl.
It's really this here. The CHO is a common ending for what functional group? Aldehyde. Standard condensed version of aldehyde. It really can't be anything else. You have the CH2, CHO. I already said it can't be COH. If it was, why didn't they just say COH? If it was COH, this carbon would only have 2 bonds. Really, the H is on the carbon, and then the other 2 bonds are to the oxygen. And there it is, C double bond O, carbonyl H. Carbonyl H. It doesn't matter how you draw it. Carbonyl H. Aldehyde. So that's standard condensed. How do we do on that one? Now, of course, you can draw this line bond, and it's boom, boom, boom. What we got here? Boom, boom. 2 methyls, CH2, O. I prefer to draw in the H in my aldehyde. It looks naked without the H to me. You don't have to draw in the H. Those are the same thing, right? Now, of course, in many of my answer keys or problems, you'll see instead of CH3, I'll write Me. Me. It just means methyl. It's a 1 carbon CH3, right? Okay. How about this over here? We got a CH3 on a carbon, it looks like. Carbon with a CH3. This carbon apparently has what? 2 methyls. And then what is this?
Carboxylic acid.
Yes, this is condensed for carboxylic acid. Or sometimes you'll see it OOH. They could have condensed this like that. That's a carbon with 3 methyls. Carbon with 3 methyls. It could have been, they could have did that a little bit differently. They could have had just one carbon and put 3 methyls in parentheses, like we did up here. Of course, this is just that, right? Of course, you want to draw in the H on your heteroatom. So, condensed formulas, 2 very common aldehyde and carboxylic acid condensed. Classification of carbons. This is no different than when we did like secondary amines or primary amides. This is a secondary amine, right? Nitrogen bonded to 2 carbons. The primary amide because the nitrogen is bonded to 1 carbon. Okay? We've really already done that. You can also do this with carbons. And if you look at this plain alkane, we can identify the carbons as, for example, this is primary carbon. Why is it primary? Because it's bonded to just 1 other carbon. That's a secondary carbon because it's bonded to 2 carbons. That's a tertiary carbon because it's bonded to 3 carbons. And that's a quaternary carbon because it's bonded to how many? 4 carbons. Okay? So it's very standard. But now we can ask questions like, hey, how many tertiary carbons are in this compound? And it looks like it's just 1, right? 1 tertiary carbon. We can also classify the H's, calling them a name based on what type of carbon they're on. For example, the 3 H's on this carbon could be called primary CH's because the carbon is primary. And the H that's on that carbon right there, which you see, that would be what? That's a tertiary CH because it's on a tertiary carbon. Now the H is always just 1 bond to carbon. But we call it based on the substitution pattern of the carbon. How many primary CH's in this molecule? How many primary CH's in this molecule? 5? No, so way more than that, I think. 15, right? 15? There's 3 there, 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 there's 15. How many secondary CH's? This would be number of H's on secondary carbons.
2.
So that's a secondary carbon. You see any other secondary carbons? No. How many H's on that carbon? 2. 2. How many tertiary CH's? 1. How many quaternary CH's? No such thing, because if a carbon is bonded to 4 other carbons, it can't be bonded to an H. And hopefully that molecule has a total of 18 hydrogens. Since it's a hydrocarbon, there's none on like oxygen or nitrogen or whatnot. They're all H's are on carbons. So this is just some classification, a little bit of nomenclature, terminology. We're doing a few miscellaneous things right here. Reactions of alkanes. Okay, this is it. Alkanes are pretty boring when it comes to reactivity. You can burn them. Of course, that's a hugely important reaction or combustion. We take butane, we can react it with oxygen. We have to supply like a little spark initiator, and we can produce CO2, water, and heat. All carbon bonds are cleaved, and the carbons are oxidized. You can balance this if you want. Importantly, we can heat our homes, or we can heat our gas grills or something if we use propane. Okay. This reaction is a radical oxygenation. It's hard to look at a mechanism for this. It's just a pretty straightforward sort of reaction of alkanes. Looking at it very simply. Another reaction of alkanes is radical halogenation. That's a radical oxygenation, most likely. Radical halogenation, we take such a compound, react it with bromine and a little light energy. We can do a substitution reaction. We can replace this tertiary CH, the bromine, and the tertiary CH can pair up with the other bromine and make HBr. So the H was replaced with bromine substitution reaction. We'll actually look at the mechanism for such a reaction near the end of the course. We can show a well-defined mechanism for this. This is much more selective. It's just one equivalent. Where up here, every carbon gets oxidized multiple times and you get bond cleavage, and it's much more complex. This is a very important reaction for taking a very simple hydrocarbon and getting like a halogen on there. From there, you can do lots of reactions, and we'll cover those reactions during test 3. Lots of stuff you can do with these. That's about it for alkanes. When we get to alkenes, test 2, there'll be tons of reaction because the alkene pi bond is a great source of reactivity. Tons of reactions with the alkenes. Okay. Cycloalkanes is a particular type of alkane where we have a ring, cyclic ring, variety of sizes. The smallest ring is going to be your cyclopropane. All of these are named cyclo, and then since it's 3 carbons, it'd be propane. Cyclobutane, cyclopentane, cyclohexane. 6. Sometimes I'll write the size of the ring in there just to be quickly identified. Okay. You can have larger stop signs or cyclooctanes, right? Okay. We will focus in on cyclohexanes because we'll look at their so-called conformations, substitution patterns, etc. Starting down below. Very common at the introductory level to look at the conformations of cyclohexanes. 9th grade geometry tells us that this bond angle is what?
60.
Looks like 60 degrees. Okay, well that carbon's, there's 2 H's in it, right? Carbon is supposed to be sp3, which is 1 of 9.5. Or 9.5, but we got it at 60. That produces a lot of strain on the molecule. Strain is a very generic term. Basically, the electrons are being forced together in the bonds. Okay, we call that angle strain. Some beginning students say, well, can this even be formed? Actually, yes, it can be. Actually, a lot of drugs contain cyclopropane rings, which is on one of the sheets in the handout. But it does suffer from so-called ring strain. And so it's a little higher energy, but it still can be made and exist. Cyclobutane has here 90 degrees. It still has some angle strain. Your best size rings are your 5 and 6. These actually have the closest to 109.5, and 5 or 6 are your best size rings. I don't show any larger ones, but when you get larger, your bond angles actually have to spread open. And that makes them not as good. What's your best size rings? 5 and 6. Today, next March in organic 2, they'll still be the best size rings, okay? They have the best bond angles there that are more approximate to 109.5, which is the desired bond angle for sp3 carbons. How can we tell the angle strain here? One way to tell is to look at the heats of formation. This is a table with heats of formation. Ignore this over here. Look right here. Heat of formation is the amount of energy that is taken up or released when the molecule is made from the elements. Okay, it's a theoretical calculation starting with the elements. For example, if you made cyclopropane starting with carbon and hydrogen, okay, so you would take C plus H2, and you would get cyclopropane. You can balance that if you want. Obviously, you need 3 carbons, right? You can balance it out how to balance equations. But once it's balanced, you can say this yields that. And then what's the heat? Do you also get heat, or do you have to put heat in? Well, look at this. For these two guys, you have to put heat in. That is, the delta H, well, the heat of formation, which is a delta H, you have to put heat in. But the other ones, you get heat out. Why do you have to put heat in to make these?
Because of the strain in the box.
Because they have strain. It's like if you were going to physically make these from models and you wanted to say, okay, let's make the bond, you'd have to, I got to put some energy in to get that to, okay, I put that energy in. Now it contains potential energy. You have to put heat in to get these to form. Where the 5 and 6, when you make them, you actually get, it releases energy. Because very often when you make a lot of covalent bonds, you release energy. But not so for these two. But these numbers can be kind of determined in the lab. Okay? Now, why are, when you get big rings, does it not become, what do we want to call it, endothermic? Didn't I say that these were not good also? The problem is you got multiple things going on. Yes, these angles may be too broad, but you're making so many carbon-carbon bonds that kind of skews the numbers. And that's what they're trying to get at here, and it gets a little convoluted. Basically, what's a heat of formation? Why do you expect these to be positive? What does it mean if they're positive? That's the main thing to get out of this. And so we can actually quantify and get some numbers to show that those two are higher in energy compared to the 5 and 6. Questions about that? Again, there's a page on the next one that shows a number of drugs that contain cyclopropane rings. It's actually a very astonishing number of drugs. I've actually been trying to collect, every time I see a drug with cyclopropane, I'll add it to my list. And I'd actually like to try to write maybe a short little paper sort of detailing this. I've never seen any papers sort of focusing in on cyclopropane and the drugs. Sort of make a catalog of them and discuss that. Why? Why is it so useful? Well, that's a different topic for another day. Okay, let's focus in on cyclohexanes, particularly disubstituted. Okay. You have disubstituted, for example, two methyls. The two methyls can be adjacent to each other. For example, if you named this, that would be a cyclohexane. And you have two methyls. What's the one position?
The first methyl.
It would be 1, 2. So this would be what? 1,2 dimethyl cyclohexane. Okay. Well, what would this be? 1,3 dimethyl cyclohexane. And this would be 1,4 dimethyl cyclohexane. What's the relationship between these three compounds? They all should have the same formula, right? What's the formula real quick? 6, 7, 8, what is that? C8, H, how many H's real quick? 8. Not 18, is it? 14. Not 14.
16, 18.
It'd be 16, right?
Oh,
Yeah.
How many DUS do you see?
1.
1. What's saturated for C8?
18.
18, but I see 1 DUS. That's 16. Now you can add them up. If I'm wrong, you can buy me a steak dinner. Okay, these are all constitutional isomers, right? Same formula, different connectivity. Here the methyls are connected at the 1,2 position. Here they're connected at the 1,3 position. Okay? Those are constitutional isomers. Right? What are these two guys? Well, that's 1,2, that's 1,2. This illustrates the idea of stereochemistry. These carbons are tetrahedral. 2 in the plane, 1 forward, 1 back. What's going back here? H. What's going back here? H. I drawn H's. 2 in the plane, 1 forward, 1 back. 2 in the plane, 1 forward, 1 back. Here, the methyls are both forward. They could be 1 forward, 1 back. But when they're both the same side, that's called cis. Now that's also the same side, but that's where they're both going back. So they're both cis. Now what's the relationship? Well, hold on. These are actually the same compound. And when we get to stereochemistry during test 2, this will become more clear. Look over here. One going forward, one coming back. One going back, these are called trans, which is synonymous with opposite. Okay? These are called trans, and you can have it this way or this way. Now in this particular case, these two are different compounds. These two are the same. Don't need to know that now. That's test 2 material. But what's the relationship between these two? Now we've got to be careful. This looks like a resonance arrow, but I'm just looking at these two. What's the relationship? Are these constitutional isomers?
No.
This is 1, 2. What is this? 1, 2. They're connected both at the 1, 2 position. Projection does not change connectivity. Okay? These have the same connectivity. In fact, if you name this, this would be what? 1, 2 dimethyl cyclohexane? What would this be? 1, 2 dimethyl cyclohexane. It tells you it has the same connectivity. They differ only in their orientation. This one would be called cis. That would be called trans. If compounds only differ in their projection or orientation, they're called what type of isomer?
Stereoisomers.
Stereoisomers. Stereoisomers have the same exact name. They only differ by some type of descriptor in front of it, like cis-trans, or erythrithreo, or something else down the line. Okay? Stereoisomers have the same exact name except for a descriptor. Okay, down the road we'll be able We'll figure out why these are actually different, why these are the same. Since these are different, you're going to have a second descriptor to determine these apart, because just saying trans doesn't tell you which one we're talking about. That's testometry. Okay, there's some drugs with, well, that's more than cyclopropane. It's also got some cyclohexanes. Look at this, fairly simple molecule. Yeah? Cyclohexane, got this primary amine, got this carboxylic acid. Okay? That's a drug that's used for epilepsy. Okay. Last two major topics for test one is conformations of alkanes and showing Newman projections, and then conformations of cycloalkanes doing chair conformations. Let's look at Newman projections, also called circle, circle, dot, dot. Remember circle, circle, dot, dot? Or is that just the names? Okay, let's look at a compound here. Let's look at ethane. Top right, ethane. 2 carbons, and let's pretend each bond is to an H. Okay? 2 carbons, H. Tetrahedral, etc. First off, between the 2 carbons is a sigma bond. Thus it can rotate, right? Okay? We could spin this in. Sigma bonds can rotate. Now, since it can spin, the question becomes is, well, is it going to prefer to be like this? Or is it going to prefer to be like that? Or what? Now, this thing may be spinning around all the time. But what we can ask is, what is the favored position? Or the favored conformation? These are just different conformations. Also, how do we draw this on the board? And on paper. Okay? The sawhorse is one way to try to draw it. Top right. Now there's some liberties there. It looks like the front carbon, everything, that H is straight up. It's not actually straight up. See, it's actually coming out at you. And the one in the back, very top, look, H is going down. That's one way. That's called a sawhorse. Okay? I'm not going to show that anymore. But you may see that like that. You'd be able to draw it like this. Let's look at the next page, though. These are your Newman projections. Circle, circle, dot, dot. I'll take you through and show you how to draw these. Let's first look at some terminology as we rotate here. We may need to draw it first. Let me hold it like this. And let me rotate maybe the back, and then we'll go back and look at it again. If this is like that versus like that. That. What do you want to call these conformations? That one is where the H bond is directly behind the H bond in front. For example, if I look through there, I can't see the one behind it. So if you look through there, can you see the one behind it? You're not supposed to be able to. So if I turn it like that, now you can see the bond behind it. What do you want to call it when it's like that? It's like the moon behind the sun. Eclipsed. Okay, that's called an eclipsed conformation. Now if this rotates, it's no longer eclipsed. What might you want to call that?
Staggered.
Staggered, if you've already looked at this. It's called staggered. That makes sense, right? Okay? Let's rotate the back 360 degrees. Now we'll start out eclipsed. Now we could do this an infinitesimal number of times. I could rotate, boom. Every one of these could be a different conformation. All right? But what we usually do is we rotate 60 degrees. Okay. Let's rotate 60 degrees and look at it like that. To rotate 60, we went from eclipsed to what? Staggered. Here's the original. We're going to rotate all the way around. Okay. Staggered. Let's rotate another 60, and what do we get back? We get eclipsed. Of course, it's now a different H eclipsing that up there. Now we get what? Staggered, and we've rotated 180 degrees. Now we get back eclipsed, and then we get back staggered, and then rotate the final 60 degrees. We get back to eclipsed. Let me ask you, is this eclipse any different from this eclipse? It's actually not, because these are all H's. Okay? This is what we just did, and we went through and we can actually plot potential energy. For example, the eclipsed is higher in energy than the staggered, because when it's eclipsed, these electrons are closer together. And so if we start here, and let me draw this for you, okay? This is if you're looking straight through here, like you're looking at. What do you see? You see a carbon with 3 H's, and then behind it you see another carbon with H's. So this is behind it. Okay? This is the front carbon. The back carbon you can't see, but you can see those H's coming out from off that back carbon. Let me show you how you draw these. Basically, can you draw, can we draw that on the board? Like that. Start with a circle, with a dot in the middle. And the dot in the middle is your front carbon. You've got an H going straight up. Okay? Now, it's not exactly going straight up. It's actually coming out towards you some, right? But we lose that. Okay, you just have to know that it's really tetrahedral. Okay. You've got an H going to the right and a little bit down. And you got an H coming to the left and a little bit down. There's your front carbon. Now the back carbon, which is behind this circle, it's like this here makes a circle, so you can't see behind it, but you can see this H coming straight up. Now, it's really right behind that H, and you're not supposed to be able to see it. But we draw it just a little bit to the side, and we draw it coming out from the edge of the circle. It's like in real life, this line is right on top of the other line. And those H's are eclipsed. Now, since I drew this back a little bit to the right, I'm going to draw this a little bit to the right. And so I'm going to show this. Okay? And that's supposed to be what they have here. Although they drew their H in the back a little bit to the left of the front line. Either way works. Now, and that's high, this is just relative. This is higher energy than net. Because this is eclipsed, right? All those up there eclipsed. Eclipsed is always higher in energy than staggered. Always. These are all staggered. Did they rotate the front or the back to get to this? Yeah, they rotated the back. Because now this guy has the H, it's like that. They're rotating the back as they go through. Okay? Now I'll just draw this again. I don't know if it's useful for you to or not, but let's see. I'll rotate the back. I like to kind of indicate I'm going to rotate the back. Now the front I didn't do anything with, so I'm going to just draw it the same. Now the back, I rotated 60 degrees. This H is going to be right between these two. But it's coming out from here, right? We're actually, they're all going to be like that. This was the second one. So they're rotating the back 60 degrees. If they rotate the back another 60 degrees, what do they get? They get this eclipse. But that eclipse is no different from this one. Because an H eclipsing an H is the same as an H eclipsing an H. Okay? And we go through, and if we go all the way around and do a complete turn, this is actually back over there. If this is A, isn't this A again? I think that's back to A. Staggered, eclipsed, staggered, eclipsed, staggered, eclipsed. Yeah. Those two, they're back to the same. Potential question here is how many different energy levels are shown? Different energy levels. There's only 2 energy levels. Okay? So this is the same energy level. You got this energy level, and you have that energy level. Eclipse versus staggered. Drawing these. Now let's look below, and what if we change to butane? Now to get to butane, I'm actually going to take off these here. And now I'm going to say that that's a carbon, 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 carbon. 4 carbons. Now I'm going to say the H's are the 2 little tiny little points here. So now we have butane. Sigma bond here, so we can rotate. How are these methyls going to like to be? First off, what do you want to call that conformation? Eclipsed. These bonds are eclipsing. And that would be staggered. What do you want to call this conformation? The CH bond is eclipsing the carbon-carbon bond. And actually, if we look over here, carbon-carbon bond is eclipsing the CH bond. Okay? So that's actually also eclipsed, but it's not as bad as this, because here, your large groups being on the same side is not good. Because remember, these are methyls. There's H's coming off. And if we drew these in, it'd be larger volume up here, and this volume would be sort of interacting with each other. Okay. Basically, this scenario is going to give us more energy levels. But what do we call the energy levels? We also have new terminology. Let's start with A, which is that there, right? Front carbon, we have a methyl straight up. Back carbon, you have a methyl straight up. By the way, dihedral angle, let's mention that. What is a dihedral angle? Dihedral angle is it's 2 different planes. It's the angle between a bond on the front carbon versus a bond on the back carbon. For example, right here, this is a dihedral angle of 60 degrees. Right there. What's that dihedral angle? $90 degrees. Okay? It comes from here. There versus here. What's the angle? It's the same as if you moved that there. What's that angle? 90. We'll pretend it's back here. Okay? You forget that. What is this angle? Yeah, it's just 2 different planes. Okay? What's that dihedral angle? 0. That's 90. What's that dihedral angle? That's up. This is straight down. Okay? You can join the planes together. It's 2 different planes. That's called a dihedral angle. See And this has a 0 degree dihedral angle. It's supposed to. There in the view, it's okay. That'd be 90. It's supposed to be 0, but if we drew it exactly 0, you wouldn't be able to see behind it. Then your view would become a little bit uninterpretable. Okay. Let's go through this. What do you want to call this? First off, it's staggered. I'm sorry, not staggered, eclipsed. Okay? Eclipsed. And that's A, B, C here. Let's rotate this 60 degrees. What do we have?
Staggered.
We have this. Okay? This is B. Need to go through these and we'll pick up here next time. Staggered or eclipsed?
Staggered.
Staggered. Okay? But importantly, this staggered is different from this staggered. So we have to have names to distinguish between the different staggers. Okay guys, this is what I want you to do. Please look through this. And then please show in the middle of the blue sheet, show those 3 in the lowest energy Newman conformations. Okay? In your textbook there should be instructions for showing these. Importantly here, you want your largest groups to be anti. Okay? Largest groups anti is your best lowest energy conformation. Okay, in lab Thursday, tomorrow we'll meet downstairs unless I tell you otherwise. Have a good day, guys.
You ever you know how you're talking about that? You ever refer to